So our next speaker is from the SDG, Vladimir Perejogin. Vladimir joined the SDG 20 years ago, and he has a master's in physics, and he has also completed a defense fellowship with the U.S. Air Force Research Laboratory. Vladimir currently leads the Advanced EO Systems discipline for intelligence, surveillance, and space division for electro-optic infrared techniques at the SDG.
All right, so today I'm going to talk about a world-first neuromorphic EBS sensor technology demonstration on board the Defense Experimentation Airborne platform. EBS is a versatile and low swap and cost technology, and it has great potential for long-range surveillance applications. The preliminary data from this airborne trial will highlight some of the key advantages for maritime and urban target detection and tracking. So what is neuromorphic event-based sensing? Some of you may have heard about this and heard about it a lot and wondering what it actually is. Well, it's a biology-inspired sensor to mimic the behaviour of the human eye. We give it the name neuromorphic because of the nature of the data that it produces and the fact that coupled with a digital cortex type processor or a neuromorphic processing algorithm on the back, you have a vision system that replicates something akin to the human eye and the brain working together. They sense intensity changes in light rather than accumulation of light in the way traditional frame-based images work. So if you take the example of a spinning wheel, if we can see up there, if you imagine that wheel rotating around, a conventional camera is just going to image and snapshot image that dot on that wheel at discrete intervals in time. An event camera effectively only senses the change induced by the motion of that dot, and it produces a continuous stream of data at a very high temporal rate. These sensors also have a very high dynamic range, basically what they do is they produce data that effectively is a location of where that change occurs in a pixel, the polarity of that intensity change, if it's an increase in intensity or a decrease, polarity tells you which way it's going, and a timestamp for when that occurred. And if there are no changes induced on a pixel, then you simply get no data. You simply are only detecting things that are changing. So some of the pros and cons of these sensors, and something that we've been looking at in a little bit more detail, is really on the benefits side from an Earth observation or an airborne ISR perspective, is low cost, low size, weight and power, high dynamic range, fast temporal response, assuming we've got some good illumination there, and lower data rates for unclouded scenes. Because of the speed of the device, it's less affected by platform instabilities, vibration, jitter. And the other unique advantage is that it detects change in motion, something that a traditional sensor, if you're using it in an airborne ISR type application, requires a significant amount of pre-processing to understand what the background is doing. You have to difference that information away and you have to look for anomalous behaviour. The event-based camera just natively produces those outputs without any pre-processing steps. Some of the limitations at the moment, these sensors were developed out of academia going back 15 years or so ago, particularly in the overseas European markets. We talked about supply chain issues throughout the conference. This is one of those things where if we deem this technology to be a capability that we want to adopt, we really need to think about those supply chain issues for the technology. And that's why we have programs such as what Greg Cohen is running to develop sovereign EBS development capabilities in-house. And that's a way of trying to develop the capacity to overcome some of those issues. As I mentioned before, the temporal response is fast, but at the moment these are intensity-dependent features. So in poor light scenes, the response time is actually quite a bit slower. If you have really bright changes, the temporal response increases significantly. The other thing that's important to understand here is that the current state of art in this area is wavelength limited to the visible band. So that just immediately pushes the sensor into a particular operating mode. And if we want to start thinking about how we might use the technology to sense things where we don't have natural sunlight illumination or artificial illumination, we need to think about some of the thermal emission properties of objects and things like that. So that'll shift our waveband into, say, the infrared domain. So just a brief history of neuromorphic innovation, EBS innovation across defence, and the activities that DSTG as a whole has been plugged into, not just necessarily my team, but other teams across the organisation as well. We've been involved in a number of S&T capability development activities, a lot of collaborative programs and partnerships, and providing advice and support to key EBS sensor development activities, including in the early days with space situational awareness applications, multi-band sensor trials, some work in neuromorphic event processing for SPAD LiDAR. There's some engagement with initiatives like the M2 mission that's hosting an EBS payload. And I know Greg is plugged into the USAFA ISS Falcon Euro project as well, also another EBS sensor in space. We're really interested in exploring opportunities to look at that data and assess its mission utility in a defence context. And some of the more recent things, such as the SmartSat CRC initiatives to do space jeopardy and response projects, basically looking at whether an EBS could be used to detect debris that's incoming that might affect a spacecraft, and some industry-led EBS demonstrator projects. So overarching this, the alignment of the work that we do in this area is strongly aligned with DSTG Starshot missions, innovation initiatives, and allied collaborative activities. So we move on to the Airborne Trial. So this was enabled because DSTG owns something called the Defence Experimentation Airborne Platform, the DEEP. This aircraft is a key enabler for ISR research and development. It's capable of hosting high-end sensor capabilities with an emphasis on end-to-end integrated ISR, and it allows us to demonstrate utility in a highly mission-focused scenario, or highly mission-focused scenarios that are operationally relevant. And so given the nature of the EBS sensor being a low SWaP sensor, it was easy enough for us to quickly integrate that into the DEEP and run orbits up and down Adelaide and collect data to basically integrate that system and co-locate with an existing wide area motion imagery sensor, collect some interesting and relevant scenarios, and demonstrate the utility for ISR and enhancement over frame-based cameras. So here's an example of what the data products look like. On the left-hand side, we have a cropped image of the wide area motion imagery sensor, and on the right, we have an EBS product. And the right, unfortunately, is going to stop playing for a minute. But what we effectively see is we have a bunch of motion clutter in the frame-based camera on the left, and we see a lot of features from the water structure and a lot of thin cloud drifting across that scene. Whereas on the event-based sensor, these have little effect on that camera. And we're also pointing out that what we're picking up is really the contrasting features for the boat wake and the vessels that are stationary in the water. And everything else in the scene is effectively, there's no data present there for it. If we were to try and do that with the frame-based camera, as I said earlier, we need to do frame registration, we need to do background differencing, we need to look for statistical outliers. In a maritime concept, that's really challenging because to do frame registration, you need features, and those features aren't necessarily present. So for reference as well, a lot of these objects in the water, we do have complementary data and AIS data that we collected on this activity. However, a lot of these vessels are small recreational fishing boats. They don't operate AIS transponders on them. This next example is an urban environment collection example. And effectively what we just did here was to explore some simple stabilisation techniques, and the purpose of this was to highlight the movers in the scene. So the left-hand side is just the native event-based camera output, and the right is just taking that information and trying to stabilise it. And what we see is a lot of the vehicle traffic moving up and down the highway, cars and trucks and the likes. So the key initial findings for the experiment, whilst it's, we could say, well, how is it different from conventional sensors? Well, the one big advantage here is that they are extremely low swap and low cost. And to give you an example, an EBS camera like this costs about $5,000. A full motion video EO turret or something like that on a maritime platform is about $500,000 plus per unit. So straight away, you've got a capability that's cheap and able to perform a very similar function. We can also capitalise on platform instability to easily detect contrasting edges in the scene, and this would alleviate. They also alleviate pre-processing techniques that you would employ for traditional video moving target indicators. EBS simply skips a lot of that, so you get that advantage straight away of being able to detect motion. And finally, we have a very rich data set, including the wide area motion imagery, higher resolution data there to support algorithm development. This is there to help support event data stabilisation, image fusion, and training data for deep learning techniques. So what next? As I said, I think data processing is where we really want to start exploring the utility. How do we take that sensor, which, even if we were treating it as a commodity sensor, how do you bring processing and exploitation into it and package up not a commodity sensor, but a commodity capability that defence can use? And this is to support real-time efficient edge processing for automated decision-making. The other challenge we have here as well, we talk about innovation a lot and the innovation cycle. We really like to encourage, how do we as a community develop that framework so that we have the opportunity to off-ramp good ideas out of innovation and then on-ramp it into a capability acceleration activity where we take the good idea, we transition it into an operationally relevant capability, and we deliver that impact to defence. And I'll stop there. Thank you very much.
Thank you.
And I'll take any questions.
Any questions from the audience? Yes.
Yeah, sure. So the question is about the claim that they're less susceptible to jitter. However, we do see products here that look like there is jitter, and we're trying to figure out how to stabilise that and remove that. The comment about being insusceptible to jitter is about the fact that the camera can record data very quickly, and so it records the jitter profile effectively. So in the example where you would have seen that scene, the urban scene, and a lot of edges being contrasted, a conventional camera would just have all of that information smeared out in the frames. With an event-based camera, and in fact when we flew this, we can run a real-time process on that and extract the vibration frequency profile of the camera. So having that ability to understand that means that we can have a processing there to counter it.
So it's less susceptible to ego motion because it's so easy to determine the ego motion and remove it.
Correct. Yeah, so the question is about what's the TRL of the technology at the moment. So I'd say, as the sensor itself, if we go back to, the very early picture here, right up there we have, this is the camera itself. It's a 50mm by 60mm camera, right? You would call the TRL of that camera very high. Where the TRL is low is the capability and the application of that sensor for this particular mission. And so that's why I talk about you know, in the context of what we're trying to do here, we're trying to be smarter about how we use the sensor, and that's not just about the camera itself, it's about wrapping all the processing behind it. And it's that piece where, you know, we're going to start seeing a lot of value out of this type of technology because it is clearly overcoming some of the limitations of fundamental imaging.
I think we've run out of time. Let's thank Vladimir.
Thank you.